Hello, my name is Qichang Han and come from the Electrical and Computer Engineering Department. Today I will talk about the OFDM channel estimation based on the pilot. Okay, here's outline. I will introduce OFDM and the fundamental principle of OFDM system and the OFDM channel estimation based on pilots, the MATLAB simulation, and the last one is the future work. Okay, the OFDM is a kind of multi-carrier modulation technique which splits the single physical channel into several orthogonal subchannels. The OFDM has been a key technique in the fourth generation mobile communication system. Here is some several advantages about the OFDM. The first one is the high spectral efficiency. The second one is the high ability to resist the multipath interference and the frequency selective fading. The third one is the high ability to reduce impulse interference and the narrowband interference. The fourth is it's able to decrease the system complexity. Okay, the disadvantage about the OFDM is that it's very sensitive to the frequency of sight and phase noise. And also the peak to average power ratio is large and therefore results in low efficiency of amplifier power at the receiver. Okay, now I will talk about the fundamental principle of OFDM system. Here is just the flowchart. First, we do the channel coding for the binary data in order to reduce the error rate of information at the receiver. Then we just utilize the QAM or PSK modulation to map the binary data into the different phase of carriers that are suitable to transmit data in the channel. After the mapping, we just do the serial to parallel conversion, and we know that the symbol period is very small due to the high data transmission rates. So if the multipath delay occurs, several subsequent symbols may be affected. So after the mapping, we do the serial to parallel conversion to split the high data streams into n-low data streams, and therefore the data symbol period is n times larger than original period. So the RSI, which means the intra-symbol interference, can be reduced effectively. So after the SP conversion, we just insert the pilot and do the IFFT, which means the OFDM modulation. So in the next section, I will mainly discuss the OFDM modulation and the demodulation. Okay, after the orthogonal, according to the orthogonality of the subcarriers, we just got the equation 1. From this equation, we know that if the m is equal to n, the result is 1, otherwise the result is 0. And we just suppose that n-low data streams carry n information, which means S1, S2, and so on, and every information is modulated into the corresponding orthogonal subcarriers, and we got the equation 2. Okay, in the receiver, different subcarriers do the inner product with the received signal, and we can get a sub k, which is shown in the equation 3. From this equation, we know that the information at the transmitter can be accurately demodulated at the receiver from a group of signals. However, if we want to obtain n orthogonal subcarriers, 2 n oscillators are needed, which is hard to achieve in the engineering practice. So we have to think about another way to resolve this problem. Okay, we defined the frequency spacing .f, and we got the f sub k, and we defined the time spacing, sampling spacing t sub I, and we got t. So we do the sampling for the signal, and we got equation 4. So after the careful observation, we will find the equation 4 is the IDFT, which means the discrete inverse discrete Fourier transform, and As the receiver, we just do the discrete Fourier transform to obtain the demodulated information A sub k, which is shown in the equation 5. So in the practical application of OFDM system, we can utilize the IFFT or FFT to replace the IDFT or DFT because the IFT or FFT is more convenient and efficient. So after the IFT, we just insert the cyclic prefix. And but first I will discuss the graph interval. We have known that the serial to parallel conversion can alleviate the RSI effectively. In order to eliminate the RSI, we are able to add graph interval in front of the OFDM symbol and also make the length of graph interval larger than the maximum delay surprise of the wireless channel. But if the graph interval is empty, the ICI, which means the inter-carrier interference, cannot be resolved, and the orthogonality will be destroyed. So we add the cyclic prefix and make sure the time width of graph interval is larger than delay surprise of multi-channel. And okay, this picture is just the cyclic prefix. And TG and the TG section is cyclic prefix, and this part just copy the latter parts of OFDM symbol and then put it into the front. Okay, due to the introduction of cyclic prefix, the OFDM symbol has the property of periodic cycle within the integral interval, and therefore make sure the orthogonality of different subcarriers. Consequently, this method is able to eliminate the ICI. Okay, in the next section, I will just talk about the OFDM channel estimation based on palette. The first I will discuss its importance. The wireless channel is very random and will lead to the distortion of amplitude, phase, and frequency, which makes it easier to cause the RSI and therefore limit the development of mobile communication system. So in order to improve the performance of systems, the exact information of channel is key point. For example, adaptive channel equalization can resist the influence of RSI through the channel information, and the coherent demodulation achieves the signal detection by channel information. So the accuracy of channel estimation is very important. Here I just want to talk about the structure of the palette. The first one is the block palette. So in the block palette structure, all the subcarriers of OFDM symbols can be inserted palette, and other symbols transmit data information. Palette symbols are able to resist frequency selectivity fading effectively because palette symbol cover all frequency. Also, the block palette structure is sensitive to the fast change of channel and therefore is suitable to the slow change of channel, which means the channel is stable during a certain time. Okay, the second structure is the cone palette. For the cone palette structure, the palette can be inserted into the specific subcarriers of the OFDM symbol, and this kind of structure is suitable to the first change of channel. And if utilized to do the channel estimation, we not only need to estimate the channel response as palettes, but also channel response of other symbols via the interpolation algorithm. So then I will discuss the three kinds of the estimation algorithms. The first one is LS channel estimation. Okay, this estimation just makes the cost function of impulse response vector minimum without the consideration of noise, and which got the equation 6 and equation 7. Okay, the equation 6 is just the impulse response vector, and equation 7 is the code function. And we just suppose this formula is equal to 0, and we got the LS equation, LS estimation, which is shown in the equation H. So the advantage of LS algorithm is the simple structure and small calculation. However, since the algorithm ignores the influence of noise, the channel estimation value is sensitive to the noise and the ICI. So in order to overcome the influence of noise, we just propose MMSE algorithm and its improved algorithm LMMSE. MMSE channel estimation algorithm just utilize the second order statistics of channel to reduce the mean square error. We just use the RCGG, RCYY, and the RCHH to represent the autocorrelation function of G, H, and Y respectively. And RCGY represents the autocorrelation of G and Y, and the sigma square is the variance of noise. We just suppose that the channel G and the noise N are not correlated with each other, and then we can get the following three equations. Suppose we have known the R sub GG and the sigma square, and then we can get the G value and the MMSE estimation, which is shown in the equation 12 and the equation 13. Compared with the LS algorithm, the MMSE algorithm just consider the influence on the noise and have great performance to resist the noise. So the MMSE, but the MMSE algorithm needs to get the inverse matrix, and which means there will be a lot of calculation. So in order to reduce the calculation complexity, I just talked about the LMMSE algorithm. So we use this expected value to reduce this value with the same simulation method, and we got equation 14 and 15. And the SNR is just the average signal noise ratio, and we obtain the channel estimation base, and then we can obtain the channel RMMSE estimation, which is shown in the equation 16. If we have known the SNR, NR, and R sub NN and R sub HH, and this formula can only be calculated just once rather than every time. So the computation can be reduced. And we have obtained four-order LMMSE channel estimation algorithm and the matrix calculation. However, the matrix calculation is still large. So we just introduce the SVD LMMSE algorithm. The SVD is just the singular value decomposition. Since the spectral energy concentrates on the low frequency section, that is previous p orders, and we just use then the p orders and ignore the other orders. This algorithm just able to decrease order of equation 13. Okay, I will show that. Okay, this formula, and therefore simplifying the calculation further, we just do the singular value decomposition for channel autocorrelation matrix. It's shown in the equation 17, and U is the unitary matrix, and lambda is the diagonal matrix of eigenvalue, which is lambda sub 0 is larger or equal than the lambda sub 1, and so on. Then we can get the SVT LMMSE estimation, which is shown in the equation 18. Okay, lambda k can be considered as the channel energy. Previous p channel energy is larger than noise, and others are lower than noise. So we only keep the previous p channel energy and ignore others. So in a word, the SVT LMMSE algorithm can not only reduce the order of calculation but also the influence of the noise.